Welcome and thank you for joining. Let's take a look at a very special rational function. So this time we're graphing a quadratic over quadratic, and what makes this function special is the way it behaves around the horizontal asymptote. We'll start off with the domain. For the domain, we look into the restricted values of x, which are always hiding in the denominator. So we do not want the denominator to be 0, and we have to find out what values of x will make the denominator equal to 0. So 5 minus 3x squared has to be different than 0, which means that x squared has to be different than 5 over 3, and x different than plus or minus the square root of 5 over 3. So we'll write the domain right here. We can write it in set notation, it's shorter this way, or in interval notation. Now, based on the restrictions of the domain, we'll determine the vertical asymptotes of the function. So the vertical asymptotes are located exactly at the restricted value. So since there are two restricted values of x, this function will have two vertical asymptotes, which are at x equals square root of 5 over 3 and x equals negative square root of 5 over 3. So we'll write the equations of the asymptotes. Now remember, when you write the equations of the asymptotes, it is very important to write them in proper format. So vertical asymptote x equals root 5 over 3. And very often people try to or tend to not write the very important part that indicates that x is equal to root 5 over 3 is the asymptote. So do not write just the number, because that makes no sense, mathematically speaking. But I know what you mean, but still do it right. So next, we'll look into the horizontal asymptote. Now, we have visited horizontal asymptotes in the prior lessons, and we discussed how horizontal asymptotes are found by identifying or inspecting the degrees of numerator and denominator. And if the degree is the same, we say that the horizontal asymptote will be at the ratio of the leading coefficients, which in this case is 6 over negative 3. And what that means is that the horizontal asymptote will be at y equals 6 over negative 3, which is basically equal to negative 2. So for short, we'll simply write y equals negative 2. So next we'll look into the x and the y-intercept. We'll find the x-intercept by setting y equal to 0. And we've also mentioned that in rational functions, we don't make the entire expression equal to 0, because we know that when the numerator is 0, then the rational function will have a value of 0. So we simply make the numerator equal to 0 and solve for x. And that will lead us to the x-intercept. Now, I don't see this being factorable, so I will try the quadratic formula. So that means x equals plus negative 4 plus minus square root 4 squared minus 4 times a, which is 6, times c, which is 1, divided by 2 times 6. As you can see here, we obtain a discriminant of negative value, because 16 minus 24 equals negative 8. And this is a complex number or imaginary number, so it doesn't exist in real world. So, or in the Cartesian of real number, Cartesian plane of real numbers, or real numbers Cartesian plane. So we're going to say that there are no x-intercepts in this case. Let's determine the y-intercept. Y-intercept is easy to find. You just substitute x by 0 and evaluate the entire expression. Now remember, since x is becoming 0, it means that every term that has an x in it will become 0. So the value y will be dependent only on the constant values of numerator and denominator, which in this case will be 1 over 5. So practically, what we do is you substitute x by 0, 4 times 0 plus 1, and then divide it by 5 minus 3 times 0 squared. And that will give the y-intercept at 1 over positive 5, so 1 over 5. So y-intercept, everyone, here we go. 1 over 5. And there are no x-intercepts, we said, so we're going to make sure that it's in there. The next thing we want to check for is symmetry. And that helps a lot, especially with rational functions. There is a lot of analysis we have to do to finally shape the graph of a rational function. And when a function has symmetry, then it means that we are going to do half of the work of drawing the graph, because once you figure out one half of the graph, then the other half will be symmetrical about it, whether it is odd or even, right? So for symmetry, we always start off with determining the f of negative x. So f of negative x in this case would be equal to 6. Wherever you see x, we'll replace it by negative x. So negative x to the power of 2 plus 4 times negative x, and then plus 1. And this will be over 5 minus 3 negative x squared. When you simplify this, we obtain 6x squared minus 4x plus 1. And this is over 5 minus 3x squared. As you can see in here, the numerator that we obtain is not the same as in the function. Denominator is, but then that is not sufficient enough. So therefore, we're going to say this is different than f of x, which tells us that this function is not even, or it doesn't have even symmetry. So the next thing we want to check for is odd symmetry, which is basically adding a negative sign before f of negative x, which means that we are switching the signs of the numerator. So that means 6x squared minus 4x plus 1, which is in the numerator, will now have a sign of negative 1 here, so a coefficient of negative 1 here. And if we applied it to the numerator, because that's the way it works, imagine this is a coefficient of negative 1, and this will multiply the entire numerator. And this will give negative 6x squared plus 4x minus 1, which again doesn't give us f of x. So we'll say that's different than f of x, which means that the function is not odd. So this will be an asymmetrical function. So we're going to say there is no symmetry here. So with this much information, we are ready to put all this on the Cartesian plane. So we'll start off with the vertical asymptotes. And obviously, as you can see here, vertical asymptotes are in radical form. When you state the vertical asymptotes, okay, here, right here, they're connected to the domain. So when you state the vertical asymptotes, it's very important that you write the equations in exact form. However, when you have asymptotes in radical form, you want to find what the approximate value of it is in decimal form. So the square root of 5 over 3 would be equal to, I need to grab a calculator here. So the square root of 5 over 3 would be equal to about 1.29. So I will keep that in mind. I will keep this in mind so that I know where about to draw the vertical asymptote. But again, when I label them, I would make sure that I use the exact value of the equation of the vertical asymptote. So 1.29 will be somewhere in here, and negative 1.29, this is the vertical asymptote at x equals negative root of 5 over 3. And this would be the vertical asymptote at positive square root of 5 over 3. So next I will draw the horizontal asymptote, which we said is at y equals negative 2. Here comes the horizontal asymptote. And again, whenever you draw the asymptotes, make sure to label them. So y equals negative 2 is the horizontal asymptote. We have a y-intercept, which is at 1 over 5. 1 over 5 is 0.2, so if this is 1 unit, 0.2 is like 1/5 of it. So it will be a point somewhere in here. At this point in the process, we are going to have to determine the behavior of the graph. And to determine the behavior of the graph means to determine the behavior of the y values at both ends of the graph, which is at positive and negative infinity. And very important and most importantly, to determine the behavior around the vertical asymptotes on the left and right side of it. So in our case, since we have two vertical asymptotes, then we'll have to write in here vertical asymptote, the first one is negative the square root of 5 over 3 from the left-hand side. And then we're going to look into the behavior of y values around negative square root of 5 over 3 from the right-hand side. And then the behavior of the function at square root 5 over 3 from the left-hand side again, and the square root of 5 over 3 from the right-hand side. So that will help us predict the behavior of the function and draw the curve. Now, again, since this is a radical number, then what we have to do is determine the testing values that will help us figure out or predict the behavior of y. So imagine that the root of 5 over 3 is 1.29. So what that means is that negative 1.29, on the left side of it will have the number negative 1.3. So a good testing value here would be at negative 1.3. That would be the x value that we want to choose to evaluate y to predict the behavior on the left side of the vertical asymptote. Now, for negative root 5 over 3 on the right-hand side, remember that this itself would be 1.29 negative. So on the right-hand side of it, we should choose a number negative, or x equals negative 1.28. Okay, and I'm going to make it clearer here. So x equals, so that would be our testing value. Where are we here? This is the negative. Next, we are going to choose a number to the left-hand side of root 5 over 3. So this is positive 1.29. So to the left of 1.29, we have x equal to positive 1.28. And we're also choosing a number to the right side of 1.29, or root 5 over 3, which will be about 1.3. That would be a nice number to choose. I would choose these numbers first because you will find that we get so caught up with all these numbers that we have to check the y values and it becomes a little bit more disorganized. So organize the information first, know what to do, so make a plan and then continue with the evaluations. Now, remember that our goal is to find the behavior of y values at these specific values of x, or at x infinity, negative infinity, and so on. For infinity and negative infinity, because we want to have more specific value of y, or clearer or a more estimatable value of y, what we're going to do is choose a value of x equal to positive 100, so a large positive x value. And similarly, for x approaching infinity, we're going to choose a value of x very large in value, like say negative 100, and estimate y. And now we are ready to evaluate the function at the indicated points. So first we're going to start with the value of the function at x equals 100. So remember that this is the equation of the function that we are using, which means that instead of x, we'll have to substitute 100 squared, and then 4 times 100 plus 1, 5 minus 3 times 100 squared. Now remember to be very careful with the number you choose, that you have to substitute the same number for every x value. And I'm going to do this on the calculator. And again, another reminder is whenever you perform this division in the calculator, which you can do in one step, be sure that you keep the numerator in brackets, then divide, and then denominator in brackets as well. And perform these calculations more than once just to double check that you got the right number, because it's very easy to make a mistake there. So open brackets, 6 times 100 to the power of 2, and then plus 4 times 100, and then plus 1 divided by, open brackets again, 5 minus 100 to the power of 2, 3 times 100 to the power of 2, would give me a value of negative gives me a negative value here, 5 minus 3 times 100 squared. So the fact that negative 2.013, okay? So we're going to say that when x approaches infinity, the y values are approaching negative 2.013. Now, we are not interested just in the exact value here. What we are interested in knowing is whether the function will be above or below the horizontal asymptote. So number negative 2.013 is more negative than negative 2, which means that it's going to be negative 2 less than it, so less than negative 2, which means that the graph of the function then, as x approaches infinity, the graph will approach the horizontal asymptote from below. So the graph is going in this direction. So we'll do something similar when x approaching negative infinity. So we are choosing the value of negative 100. So we have 6 times negative 100 to the power of 2. And then plus 4 times negative 100. And then plus 1. And divide this by open brackets 5 minus 3 times negative 100 squared. Close brackets. And this time I get the value of negative 1.987. So if the y value at negative 100 is negative 1.987, it means that this will be greater than negative 2. Okay, so it will be higher than negative 2. Imagine that negative 2 is right here. So negative 2.013 was here. Now, negative 1.987 should be above the horizontal asymptote. So we're going to say that this would be negative 2 plus. So the graph of the function as x approaches negative infinity is going above, getting closer to negative 2, but is above negative 2. Now, in a similar way, we're going to determine the values of y for each specific value of x that we have chosen here. So negative 1.3. So again, we have 6 times negative 1.3 to the power of 2. And then plus 4 times negative 1.3. And then plus 1. And all of this is divided by 5 minus 3 times negative 1.3 squared. And the number that I obtain in here is negative 84. So negative 84 would be the value of y at x equals negative 1.3, which tells us that the graph of this function as x approaches negative root 5 over 3 from the left-hand side, the y values will be heading down to negative infinity. So we're going to draw an arrow here to indicate the direction of the y values. In the same way, we're finding the value of y as x approaches, or when x equals negative 1.28, which will give us the behavior of y on the right side of the asymptote x equals negative root 5 over 3. So let's see what we get now. So we have again 6 times negative 1.28 squared, and then plus 4 times negative 1.28 plus 1 divided by 5 minus 3 times negative 1.28 to the power of 2, close brackets. And in this case, I get 67. So it's a significantly large number considering how close I am to the asymptote. So that will make me think that when the y values are going towards negatives in here, negative 84, it means that the y value's tendency will be towards negative infinity on the left side of the asymptote and towards positive infinity on the right side of the asymptote. So what that means is that when we are on the right side of this vertical asymptote, which is this way, the y values are heading up. So the direction of the graph will be this way. Now, next we are going to check the y values at positive 1.28. Again, use the equation of this function. So we go 6 times 1.28 squared, and then plus 4 times 1.28 plus 1 divided by 5 minus 3 times 1.28 to the power of 2. And in this case, I got quite a large number. 188 is the value of it. So what that tells me is that when we get close to the asymptote on the left-hand side of it, root 5 over 3, the y values will be approaching infinity. So here we are at the vertical asymptote 5 over 3. On the left-hand side of it, the y values are heading towards infinity. So the function is going up this way. And lastly, we have to find the value of y at 1.3. That's the point that we chose. And what we have in here in this case is 6 again times 1.3 to the power of 2 plus 4 times 1.3 plus 1 divided by 5 minus 3 times 1.3 squared. So this gives negative 233, which tells me that the y value's tendency will be towards negative infinity. So on the right-hand side of this vertical asymptote, the function is going all the way to negative infinity. So right here. So we know the end behavior. I made this chart actually to kind of organize the information. So that's end behavior, and that's something you may want to do for yourself to keep track of your calculations, okay? But it's not a must, so you can do these calculations right here on the chart and indicate which x values you're taking as, or you're choosing as testing values to predict the behavior of y. And once you do that, then we're ready to sketch the graph of this function. So I'm going to start with the right-hand side in here because that's kind of easier. So what you have in here is 2 vertical asymptotes and a horizontal asymptote. So what we see for x values bigger than square root 5 over 3 is that the function, or the graph of the function, will be nested, right, in these 2 asymptotes in here. So which means that the shape of the graph will be going this way. Let me make this prettier. Here we go. Now, next, we are looking at the middle part here. We know that the graph will pass through this particular point because that's the y-intercept. And at both ends in this section, the graph is going up, which means that the shape of the graph of this function will be sort of a U shape. And this is what we are going to see in this case. Now, if you were to consider how about the function going in other directions, so let's say in this direction, that is impossible, first of all, because the end behavior is incorrect. But another thing that will make us realize, even if you by mistake found out that, oh, the y value should head this way, even if you found that by mistake, then you will see, oh, if the function goes down this way, it should have x-intercepts, and we didn't discover any x-intercepts together here, right? So this would be the graph, or the shape of the graph, or the behavior, I should say, because we're not talking about very precise shapes. So we're going to wait until we learn calculus to be more accurate in terms of the concavity of the graph and so on. Now, this is the more interesting part, and this is the part I want to talk about. As you can see, in the domain to the left of negative root 5 over 3, the behavior of the function is close to the vertical asymptote going all the way down, and then here is going towards negative infinity. Obviously, x is going toward negative infinity, and the y values are right above the asymptote, the horizontal asymptote. Now, normally we have, when we discuss the rational functions, we said, oh, so if I see that there is a point somewhere here, I would say, oh, the graph is located right here, nested in between the asymptotes. But because we see that the function or the graph has continued above the horizontal asymptote, it makes me think that the graph has crossed the horizontal asymptote, right, somehow. And then it has come back to it, right, and approached it more slowly. And these are cases that happen very often, actually. And the way that we discover that, or the way we find out about the shape of the graph in cases like this, is by being very specific about end behaviors. And I know you're right now thinking, okay, so how do I know when I write a test, how do I know that I have to look for this? So how about being a graph? I think that this is making it straight. That's why, here we go. So wouldn't I just, follow common sense and find one point and then just follow the asymptote? So practically, what we're going to do on the test is you will be asked to describe the end behavior at the vertical asymptotes and horizontal asymptotes, so that you will know that you have to look for some special behaviors around the horizontal asymptotes. But I brought in this example so that we can get to know the horizontal asymptotes a little bit better and realize that vertical asymptotes will never ever be crossed. Okay, so even when we have removable asymptotes, they would leave a break on the graph, but vertical asymptotes are not touched. But when it comes to horizontal asymptotes can be crossed. And now you're wondering, okay, but didn't we define horizontal asymptotes as horizontal lines that the graph can never touch? It gets very close to, but it doesn't touch, but it doesn't intersect them. So the truth of the matter is, yes, that is true, but remember that horizontal asymptotes are defined as values of y as x approaches infinity. It's the values of y that kind of stabilize or stop changing significantly when x approaches infinity. Okay, so at the end, right, or as x approaches infinity, they are going to serve as good guardians or good walls of the graph. But when in between us vertical asymptotes, right, exciting things happen depending on the equation of the function. I hope that this shed a little bit more light and more understanding to what we had before today in class. And I hope this makes sense. Continue practicing and try to explore as many rational functions as possible. They're fascinating. All right. Thank you for learning with me then. Bye for now.